Yeah, okay. So I start. So good morning, everybody. Thomas introduced the CCAT-prime telescope and the cosmology science cases. And I'm going to talk about the interstellar medium studies, which are comprised in the Galactic Ecology program. Because Thomas also showed that about 1/4 of the observing time will be dedicated to ISM studies. So CCAT-prime is not only a cosmology instrument. So I talk on behalf of the whole GECO and CCAT-prime collaboration, in particular work together with Robert Simon. So first of all, you may ask yourself, why do we need a 6-meter telescope for interstellar medium studies? So in order to answer to this question and motivate also CCAT-prime and the science cases, I put here a little personal and very biased list of some important findings we have done in the last decade, because surveys provided us with a lot of information. I talk of Spitzer, Herschel, a lot of the CO surveys we have. Here on the upper image, you see a part of the Herschel-Huygens survey. And here in the lower panel, the 13CO 221 survey with ARPEX. And what we learned from that is that the interstellar medium is very complexly structured. And in particular, the filaments were found to be a very important ingredient for star formation. So I refer to the work of Philippe André, of Frédéric Mott, who really emphasized the importance of filaments, of hub filament systems, etc., etc. Some results may be controversial, forgive me, Philippe, if you listen, but I think in particular that triggers even more the need for more observations and for more research in this direction, because we still don't know exactly how molecular clouds assemble from the warm neutral medium and then form into very dense structures which are cold and dense. So there's still a lot to explore. What we also learned is that star formation is a very dynamic process and can happen already while a molecular cloud is actually forming. But we don't understand what drives a supersonic turbulence that is associated with this process, if it's driven by stellar feedback processes, by gravity, so by mass accretion. So there's a lot to learn in this direction. Stellar feedback, anyway, plays a very important role. I don't need to tell you that. It is detected by, stellar feedback means radiation and stellar winds, and the cooling lines of the interstellar medium in the far infrared are extremely important to be observed. And it was basically only Sophia who provided us with the most important cooling lines, which means the ionized carbon at 158 micron and the 63 line and the high GCO lines. Yeah. But we still don't understand the relative importance of the various feedback effects. What drives stellar winds, what is the relative importance on radiation, the ionized gas pressure, on triggering star formation. There's still a lot to explore. So as I said, this is my very personal biased view of important issues. Pierre and Carl already summarized very nicely what instruments like ALMA and NOEMA can do on a very small scale. So I talk more of the larger view. And as I said before, surveys are extremely important. They progressed us in understanding better large-scale formations. So I mention here again, from infrared to radio, we have important surveys. We have surveys in hydrogen, and we have an increasing number of surveys in low GCO lines. But what is missing is an extremely important tracer, and this is atomic carbon. Because atomic carbon is very versatile. It can be, it is, of course, a tracer for UV illuminated gas. It traces photon-dominated regions and massive star-forming regions, because it is sandwiched between ionized carbon and molecular CO. But it can also trace the CO dark gas in low density regions. In addition, it can also be an indicator for dynamic processes like cloud-cloud collisions or for colliding atomic flows. But we don't know much about C1, simply because it was not often observed. There are two lines. There is a 1-to-0 line at 492 gigahertz, which is accessible by APEX and by FYST. And there is the higher line at 810 gigahertz, where it's also very rarely observed. So despite its interest and importance, there are not many maps, and not talking of surveys of C1. So I think that's very important to have this line observed on a larger scale, and I will talk about these surveys. In addition, the more classical line is CO4-3. It's a line that traces the higher excited, warmer, and denser molecular gas. There is no survey in this line, just small maps, because all the other CO surveys stopped at the 3-to-2 line. CO4-3 can also be used as a low velocity shock tracer for the lower density environment. And I will talk a little bit about these science cases. So Thomas already introduced the telescope, and in the next talk we hear about PrimeCam. A few words to CHI, because CHI is the heterodyne receiver, which will provide us with the instrument to observe C1 and CO. And as Thomas showed before, there will be two arrays, the low frequency array and the high frequency array. And you see here the frequency coverage. I don't want to go into details, but emphasize that they have a large field of view and a relatively small beam size. The instrument performance is very good. It's currently built in Cologne, and we will start to observe in the first light period in the first years in these two lines, and later going up to the high frequencies. Okay, perfect. So as I said before, CCAT-prime is a survey machine. It's a relatively small telescope, but can be very efficient in mapping because we have these 64 pixel receiver arrays. So we focus on surveys, and we defined from the science cases 3 main surveys. So one is a galactic mid-plane survey covering the plane and some line of sights. Then the out-of-plane survey focusing on individual molecular clouds. And of course, we have to observe the Magellanic Clouds and some other nearby galaxies. So I shortly summarize these 3 surveys. So we start in the beginning with some template regions. That's a must-do, because the C1 line is expected to be a very bright line in massive star-forming regions, and we want to see bright lines in the beginning. That's obvious. So we have to do Orion and the galactic center as important template regions. And then we continue to cover the massive regions which are accessible from Chang'an Tor. And this is based a little bit on the selection of complementary data, because in order to get the full carbon budget, which means the ionized carbon, the atomic carbon, and the CO, we need, of course, observations of all these tracers. And ionized carbon is difficult to get. It's Sophia who provided us in the last 10 years with C+ maps. And there's even an increasing number of maps. And we use a lot from the Sophia legacy program, which is currently running. I invite you to check here more the details. And a number of sources mentioned here are covered by feedback. So it's nice then to have these complementary data sets, because also it covers in different physical properties of the regions, different geometries, from bubbles to bipolar regions to filaments, and different masses and UV field. What we do in addition is to observe some sightlines from the GOT C+ survey that was done with Herschel, and it was C+ observations along certain sightlines along the Milky Way. And this is going to be interesting to use a comparison between C+ and C1 to judge how good C1 is as a CO dark gas tracer. Okay, so when this early science phase of individual regions will then slowly develop into a really unbiased survey of the galactic plane. That's our objective, to really cover the galactic plane accessible. And this, I think, is going to be very interesting because it will be more unbiased. And if you perform studies like that, you should always expect the unexpected. And I'm very curious to see what C1 will tell us. And in order to illustrate that, I would like to show you one example from the Sophia Legacy project from feedback, where we also found something unexpected. We observed, as I said before, C+ in star-forming regions. And as one example, I show you here the bubble region RCW 120 in Herschel. This is a line-integrated C+ map. And what is remarkable is we found, you see that here in this position velocity map of C+ emission in a horizontal cut through the region, that you see this feature here, which indicates an expanding shell in ionized carbon. And this is not a single feature we just found in this region. We find that in all feedback sources, so a number of other star-forming regions. So it's a phenomena which was not so known before. And we think that these C+ bubbles are driven by stellar wind. And this is interesting because stellar winds were always considered as being not so important for feedback processes in the ISM. We also calculated that these expanding bubbles can possibly trigger star formation on short timescales. So it's going to be very interesting to see how the atomic carbon and the CO43 are now behaving. Do we see similar features? Because C1 is also a PDR tracer. In low G CO lines, we don't see these expanding bubbles. So we're going to see. Okay, this was about the galactic midplane survey. The out-of-plane survey contains a number of low mass star-forming regions or quiescent regions. Yeah, you see Musca or Chameleon are included, which are more quiescent in terms of star formation. And here I focus on one science case we want to investigate, which is the dissipation of turbulence traced by low velocity shocks. And this can be done with CO. So I present you something from the project Genesis, actually, because in this project, together with Sylvain and Robert, we focused on investigating the formation of dense structures. And it was predicted that structure formation and filament formation requires that the turbulence is dissipated. And this can be done by low velocity shocks. And it was also predicted that the mid-G CO lines are good tracer for this process. So we studied the Musca cloud, that's the work of Lars Bonne, actually in CO 4-3. So the map we want to use for our CCAT project. And here you see the result. This is the Musca filament. And when you watch the average spectra in this small region here, you find the bulk emission at a certain velocity, and you find this excess line emission in various CO lines. And this is what we think is not excited by radiative or collisional excitation, but is an indication for a low velocity shock. And this was actually modeled by Antoine Gustave. You see here the 4-3 to 2-1 line ratio in red. And I don't want to go into details, but you see that it can be consistent with this dissipation by low velocity shocks. So we have to observe that on a much larger scale, on many more regions, to address this science case. So the last one, I will be very short on this one, is we want to survey the Magellanic Clouds and nearby galaxies. This is also a must-do because we can reach now resolutions which are not too bad for surveys. So at LMC, SMC scale, we will get a linear resolution of around 7 parsec, which manages to resolve individual molecular clouds. And we do that because we also want to expand the range of our ISM conditions. So going from the Milky Way to nearby galaxies changes the metallicity, the star formation rate. we can check how good are the various tracers for determining the cloud masses. There's a nice paper by Sue who summarized all these issues with the mass determinations. Of course, we have to model all the C1 and CO lines. This also applies for the Milky Way studies. We will investigate the variation of the C1 emission and CO in the Milky Way and nearby galaxies, and will then hopefully make also the link to a more distant and high redshifted universe. Okay, so I come to my summary. CCAT-prime is, or Fred Young submillimeter telescope, is a small telescope. It's a 6-meter aperture telescope on the Shanyantor Plateau. The Gecko Science case uses the CHI instrument, which is a 2x64 pixel heterodyne receiver operating in these wavelength ranges or frequency ranges. We will concentrate on surveys. On the galactic plane survey, the C1 and CO lines will be bright, on out-of-plane clouds, and on nearby galaxies. And I want to emphasize in my last words that I think there is a need of submillimeter telescopes at all sizes. So I think we really need survey instruments that can map very efficiently, so like CCAT-prime, but also large telescope as the IRM 30-meter and Atlas, which was presented by Claudia. Every telescope has its own purpose. Not talking of the interferometers, but that's not the subject here of my talk. I also want to emphasize that I think it's extremely important for the ISM and PCMI community to continue to observe the far-infrared cooling lines. Because what cools the ISM? It's mostly dust, but also the C+, the O1, and the high GCO lines. And to continue that, we need either SOFIA or we need balloons, but I think we need support. And for that, I would like to promote also a conference which will take place in November, and you can inscribe, which discusses the future of airborne submillimeter astronomy. Thank you. That was it.
Okay, thank you. We have time for a few questions. Jérôme?
Yes, maybe I miss it, but what will be the policy for the distribution of the data? Will it be PI only, or after some time it will become public for the surveys?
Actually, I don't know. Maybe Robert can help me in this case, because I was expecting more a question like, is it an open time instrument or not? And there I can answer, it's not a classical telescope.
This is my second question.
Okay. So I can answer that, or the second one already. It's not like other telescopes where you have a proposal and you get time, but it will be open also for collaborations. I mean, all that needs to be defined, discussed by the board. We will get a lot of data and need to digest that. So we are open for collaborations. But exactly how needs still a definition. And for the first question, maybe Robert can say something, who is online, I think.
Yeah. Hello, everybody. I'm here. Yeah, let's tackle it from that side. First of all, CCAT-prime or FYST, it's not a facility instrument. So it is basically for the community who put money and effort into this. So this is mainly the collaboration that you saw in Thomas's talk that was outlined there very explicitly. And the people who have been working on this are doing this already since a long time. And the telescope has been funded by, for example, partially funding from the state North Rhine-Westphalia in Germany through something that goes already something like 6 or 7 years back, when there was already when that was still the bigger 25-meter CCAT. So the data are proprietary for a while, but as the surveys grow, we are of course committed to also make the data public at some point. As Nicola said, we are also
Yeah.
looking for collaborations on the scientific side, because a data set like this needs to be digested, and we cannot do everything on our own. There will be a lot of people, partners coming in from Chile, because we are also kind of, yeah, I wouldn't call it trading, but as you know, every telescope has to give something like the equivalent of 10% of the observing time to the Chilean community. And for a survey instrument, that's a little bit more difficult, because we have to negotiate how this actually gets implemented and accepted then. But we are on a good way to do this. So the Chilean community will benefit right away from by participating in the surveys, and everything else should be based on collaboration, as long as the data are proprietary, and that needs to be also carved in stone and contracts and all that. So people need to be invited, but I don't think that's a big problem. At some point, as I said, the data will become public.
Thank you, Robert. Well, I propose that we move on to the next speaker, because we are running late on schedule. So thanks again.